guys, today I want to talk about electron configurations for ions because they act a little bit wacky, and it actually helps to explain a little bit about the variable charges on the transition metals on the periodic table. So we know we have main group, representative kind of elements. We have some metals over here, the alkali metals and the alkaline earth metals. Then we come into the group B, or transition metals. And then we have kind of the post-transition metals that are below the metalloids here. So these transition metals and the post-transition metals we say are kind of wacky because they can have variable charges. And I want to talk a little bit about their electron configurations today, because as we've seen, the position on the periodic table and the position of the electrons on the atoms is really going to impact the types of ions that they can make. So let's talk a little bit about electron configurations for ions in general, and then I'll use the specific example of iron for a transition metal. So let's take potassium. So what I'm going to do is I'm going to start with the fourth period here. I'm going to go potassium and calcium and then gallium. So I'm going to look at the main group elements here, and we'll talk a little bit about them first, and then we'll compare that to our transition metal. Okay, so the noble gas configuration, or the abbreviated configuration for potassium, is argon 4s1. So I went up to the noble gas before, and then I counted over into the s block, and it's 1 over. When I lose the valence electron, when I lose my highest energy electron, all that's left over is the electron configuration of argon, right? It lost that 1 4s. Now with calcium, it's the same kind of operation. So I have argon, and then 4s1, 4s2. And when I lose those two highest electrons, those highest energy valence electrons, all I'm left with is argon. Okay, so far so good. Now we know that the term for these things, when they have the same electron configuration, is isoelectronic. So this is a good reminder of that vocabulary word. So we have the same electron configuration, even though these are two different things, right? They're both ions, but they have the same electron configuration as argon, so we say they're isoelectronic. Now gallium is not isoelectronic with these, even though intuitively we think that it should be, right? Because it follows the same pattern, and we're scientists, so we're used to looking for patterns. So if we look at gallium in the periodic table, we actually have to count all the way through the D block in order to get to gallium. So the electron configuration is argon, 4s2, 3d10, 4p1. Now my highest energy S and P electrons are my valence electrons. So we say that everything in that column 3A or 13, at least those that are kind of in the follow the same sort of pattern, have 3 valence electrons, right? And that's referring to these S's and P's. So when I lose those 3 highest valence electrons, I lose them what looks like out of order, because I'm going to get rid of these 3. So what I have left over is my pseudo-noble gas core here. Now, in past videos I've said, well, you can kind of sneak this guy here. That's really where it belongs for thinking about our principal quantum number, right? Everything with the same principal quantum number is in the same shell. But we said these d electrons are kind of shifty, and because that energy level is slightly higher than the 4s, or the s that is in the next shell, there's some fluidity here, and that causes this to look a little bit different. So anything that's past the d here is going to lose the s first and keep that full d. So this is my electron configuration, which again we call a pseudo-noble gas core for my gallium. Okay, so that's just kind of a general trend. Now let's relate this to radii, because ionic and atomic radii are connected to each other, but because we're losing and gaining electrons, in this case because we're talking about metals, we're losing electrons, then these things are actually getting smaller. Recall that electrons contribute to the volume of an atom. So if we're thinking about how much space something takes up, then the more electrons that you have, the larger the volume. When I'm losing them, then my volume, or my radius in this case, is going to go down. So just to give you some numbers to compare this to, the atomic radius for potassium is 243 picometers. but the ionic radius for the potassium ion is 133 picometers. So it's a pretty significant difference. If we look at calcium, calcium is 194 picometers when it is neutral, and when it loses those 2 electrons, it goes down to 99. So again, pretty significant. And then we see a similar pattern kind of going on. The neutral gallium is 136, but my gallium 3 plus ion is 62. So the same trends that we see, so this kind of decrease going across the periodic table in atomic radius, is mirrored in the ionic radii, but were compared to the neutral atoms much smaller. Now the opposite is true for anions. So if we think about something like sulfur, and let's go chlorine too. So if we remind ourselves where we're at on the periodic table, then sulfur, chlorine. Sulfur is 88 picometers. So it's smaller because it's on that end of the periodic table, and the radii get smaller, and it's also pretty high up on the column, and radii increase as they go down the columns. Chlorine is 79. Now when sulfur becomes sulfide and gains those 2 electrons, then the radius becomes 184 picometers. So again, significant difference in the opposite direction. When chlorine becomes chloride, then we end up with 181 picometers. So again, quite large and actually pretty close to each other because they're isoelectronic with each other. Okay, so just kind of an interesting trend and an interesting relationship. And again, all related to our electrons. Now these are all main group elements, so let's shift our focus now to the transition metals. So recall that the transition metals again are in this kind of middle group of elements. And let's look at iron. Iron is in the 3D block, so the top period of the D block here, which starts with the principal quantum number 3. So as I'm counting over, so here's 3D 1, 2, 3, 4, 5, 6, and iron is not one of our exceptions to the rule, so it's going to follow the same pattern. Then I end up with this electron configuration. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. And if I was filling these into my orbital diagram, so spin up, spin down, spin up, spin down, spin up, spin down, spin up, spin down, then this first bit is all covered through argon. And then now I have 4s2, 3d6, 1, 2, 3, 4, 5, 6. So I'm spreading them out via Hund's rule. Now, in the same way that we saw with our gallium, even though we had some d orbitals in there, we had some electrons in the d orbitals, we're still going to lose the s orbital electrons first. So when I lose 2 electrons, these 2 4s electrons from iron, that's going to give me my iron 2+. So iron 2+ is going to be argon, which again gets me through all of this. And then when I get rid of these 2 electrons here, then all I have left over is 3d6. Now again, that looks kind of funny because it looks like I left some out, but I'm actually creating an ion, and with the transition metals, they lose those s orbital electrons first. Now another common ion for iron is iron 3+. Now let's think about why that is. Well, let's look at the orbital diagram. Let's think about the electrons. For these, I'm still going to lose my 4s, so here's my argon. So I've already lost 2, 1, 2 from the 4s. Now I'm going to lose that third. So now I have 3d5. Now if we think about these as being empty, right, so I don't have this orbital anymore, and now I don't have this one. Now I have all unpaired electrons here. The electrons are spread out as they possibly can. And electrons like that, right? They're going to go into each individual orbital and spread out as much as they physically can. energetically can, because it's more favorable that way. So it makes sense then that iron likes to lose these two and to lose those first three, and those are the two most common ions for this based on the way that the electrons form. Now, if we have all these unpaired electrons in here, this also helps to explain why iron is magnetic. We say that it's paramagnetic. That means that it responds to a magnetic field, as opposed to diamagnetic, which means that it does not. Now, paramagnetism has to do with all these unpaired electrons, which, because they have similar speeds, or spins, sorry, because they have similar spins, then they're all creating their own little magnetic fields there. If you have one that's spin up and one that's spin down, then they kind of cancel each other out there, and they don't create as much of a magnetic field. So the more unpaired electrons, the stronger they interact with a magnetic field. So this helps to explain iron's magnetism as well, in both its ionic form as well as its non-ionic form. Okay, so you'll see the same pattern with the other transition metals. They're going to lose the electrons in their S's first. That may look kind of confusing when you're playing around with these electron configurations at first, but then they help to explain some of the not only ions that form from those wacky transition metals that can do weirdness, but also some of the characteristics of that particular substance. If you have any questions on this, don't hesitate to reach out. Otherwise, I will talk to you again soon.